As you can see, we have very few slides over here, so this is a nice short lesson, and most people are very successful on it. Do let me know if you have any problems. But we're talking about the fundamental counting principle today. And the fundamental counting principle is essentially a way to figure out how many options you have. So if you choose one item from a group that has M items in it and a second item from a group of N items, the total number of two-item choices is M times N. Now you could find this same sort of a thing by maybe making a tree diagram that you may have done where like you say, okay, I took the first option and then I could take that with the first, second, third, or fourth and so on. But that is really cumbersome, and just multiplying is so much easier. So you're going to take the number of choices in your first selection and then times the number of choices for the second selection, and that will give you your total number of choices. Now that concept works even if you have more than two options. So if you had three options, you would just continue to multiply. So here's an example. Suppose you eat a lunch special at a place and you get a choice of meat, two vegetables, and one drink. So you're going to choose one meat, you're going to choose two vegetables, and you're going to choose one drink. So how many different meal choices are available? Well, do keep in mind, nobody said that you couldn't choose the same vegetable twice. So as we look at this down here at the bottom, I have the meat times my number of choices for veggies, times my number of choices for veggies, times my number of choices for drinks. And each one of those would be considered different. So I have two possible meats. I have 1, 2, 3, 4 veggies. But even if I choose a veggie, I still have 4 veggies to choose from because I might just tell them, well, I'd just like a double serving of green beans. So I still have 4 options there. I can choose the same thing again. And then drinks, I have 1, 2, 3, 4, 5 drink options. And so then we are going to multiply 2 times 4 times 4 times 5, that's 160. Now suppose you purchase school uniforms at a school where all the items match interchangeably. I used to work at a school like this. And so there were 3 different options for bottoms, like you could get shorts, you could get pants, you could get pants with a pleat or something, and then there's 4 different shirt options available. So how many uniform options are available? Well, this one is just the bottoms times the shirts, so we've got 3 times 4, so there are 12 options available, which means you get to tell your child you're not wearing the same thing every day, you only have to wear the same thing every 3rd week. Of course, I understand how they feel, but that's the parent's argument, right? Now, if you're going to purchase a car, there are a myriad of choices available. So we are only narrowing down this to a few of them. And to do a little bit less writing at the bottom, I'm just going to kind of count visually instead of writing it up there. 1, 2, 3, 4, 5. So I have 5 color choices. I have 2 choices for my cylinder options, 4 or 6. I have 2 choices for the transmission, 3 choices for interior, and 3 choices for the interior fabric. Now I recognize that's not nearly all the different options, so that's why this says how many different option combinations are available from just this. And I don't know why there's an S there, but just this listing. So we have 5 times 2 times 2 times 3 times 3. That's 180 different options. And we haven't even begun to really deal with the car yet on so many levels. So this is just a really nice principle to quickly find the number of choices you have. Now, when the number of choices is repetitive, so like on the last one I had 2 choices for 2 different options, and here I had 3 choices, but that happened twice. I could have used exponents, and sometimes that can really save you, particularly when we have a lot. So I could have just put 2 squared there times 3 squared. And using those exponents can save you. Here it's only just very minimal. I don't even know if it's really any writing because it was the exact same number of digits I wrote down. But if you had a lot of choices, it definitely could save you some. So look at this. If you take a 5-question true-false test and you answer all the questions randomly, you did not study, you did not know there was a test, you haven't read the chapter, whatever, you're just going to randomly hope that you get some right. How many answer combinations are there? Well, there are 5 questions, but every question has 2 choices. So that is going to be the number of choices, and then that's going to be repeated 5 times. Now, sure, you could write down times 2 times 2 times 2 times 2. But that is 32 to the 5th is 32. So there are 32 answer combinations possible. Now, I know this lesson is not about probability, but if you just start to think about how that works, what are the chances that you're going to do well in this test? Well, the chances you get the right set of choices, just randomly picking, is 1 out of 32. Should have read. Okay, here we have a 10-question multiple choice quiz, but there are 1, 2, 3 choices on all of them because it's choice A, B, and C. How many possible ways could you answer that set of questions? Well, I have 3 choices, and I could write that out 10 times, but that's going to be 3 to the 10th. So 3 to the 10th. 59,049. So that's not a very long quiz, and multiple choice is not hard to guess on, but guessing is not a good deal because there's so many possible options. And here's where I was saying, just think about it. If you guessed at all 10 answers, but only one of those answer combinations is right, what are your chances of getting 100%? This is not something you have to know for this section, but it just makes a valid point about you don't want to wildly guess. You at least want an educated guess if you have to guess, because if I did take one of those answer choices as right, divided by 59,049. This e to the -5 moves this decimal 5 places to the left, which means it's not technically impossible, but it would round to impossible because you're going to have 4 zeros in front of that. So it's going to be approximately which is almost 0. So here's another one. Suppose you have a 6-digit lock code on your home. How many possible combinations are there for the lock? Well, this is why combination locks are kind of nice, particularly those where you just, like realtors use, where you just punch in a numeric. Because here, you just kind of have to think through, well, there's going to be 6 places that we make a choice, because you have to make a choice when you are setting up your lock code for each of those digits, 2, 3, 4, 5, 6. So then the question is, for each of these 6, how many choices do you have? Well, how many digits are there? There are digits 0 through 9, which is 10 digits. And that's going to take place actually on each of them because there's nothing that says you can't use the same digit again. So we have 10 digits to choose from, and we have to make this choice 6 times. So this one is 10 to the 6, and 10 to the 6 is a 1 with 6 zeros behind it. So that is 1,000,000 choices. Chances of somebody randomly guessing it is extremely low, almost 0. Of course, those of you that have a tendency to use your birthday or something like that, that makes it easier for people to figure out if they've done any research, so don't use that. What if the first digit can't be 0? Well, if the first digit can't be 0, then we don't have 10 choices right here. We would have 9 choices for the first one, but then we could use zeros and we would have 10 choices for each of the remaining 5. So just taking the 0 out of that first digit actually lowers our value by 100,000 choices. It's pretty incredible. This is some of what is used, though, in determining numbers that we are so used to, such as phone numbers or license plates on cars. I know. So get in touch with me if you have any questions, and that finishes us for this video.